x side?
So tau on the plus x side of the square, so on this side of the square, and it's going up in the plus y direction, that represents positive shear stress. So that would represent the plus 125 megapascals. Just for the video, sorry, this is 2019 question 1 part B. So you have a shaft that's under torsion and an axial load, and we're just drawing out a stress element from the front surface of that shaft. So the coordinate system would be like this. This is the x direction, y direction, and z would be coming out of the page that way. So we're looking at the front surface of that. We're looking at the xy plane, like so. And you're given these values in the question. You're given the shear stresses of, given that the shear stress is plus 125 megapascals, so that would be represented on the stress element like this, where the shear stress on the plus x side would go in the plus y direction. That represents your plus 125. Similarly, the shear stress on the plus y side of the square is going in the plus x direction. So that's, again, plus 125. Okay, so that stress state where tau xy and tau yx are equal and opposite to each other, but they're both plus 125 megapascals shear stress. That's positive shear. Okay. So that's just kind of stating out the question. I haven't answered anything yet, but that's drawing out the stress state as described in the question. What we want to do now is to create Mohr's circle to represent this stress state. This is our original XY coordinate system. Okay? So I want to create, or I suppose what I could do first, maybe before I draw out Mohr's circle, is if I write down the coordinates of the 2 points that are going to make up Mohr's circle, everything on the x side of the square here, so that would be sigma x and tau xy, these two here are going to be the x point for creating Mohr's circle. Okay? And on the y side of the element, I'll want sigma y and tau yx. So sigma y is 0 in this case, and tau yx is 125. Those 2 points there will go up to make my y coordinate or my y point on Mohr's circle. So sigma x and tau xy, that gives you your x point, and sigma y and tau yx gives you your y point. So if we write down the coordinates of those there, my x point will be have the coordinates of sigma x, tau xy, and the y will have the coordinates of sigma y, tau yx. Okay, so sigma x here is 100 plus 100, so tension, and tau xy here. So for creating the points on Mohr's circle, I'm not so much worried about whether it's positive or negative shear. What I want to know is whether it's clockwise or anti-clockwise shear. Because both of these, tau xy and tau yx, are both positive, but one of them's clockwise and one of them's anti-clockwise. So the two are not necessarily related. What I mean is, clockwise or anti-clockwise is a different question to positive or negative. So in this case, tau xy, is that clockwise or anti-clockwise? So this pair of half arrows are both tau xy. Would they tend to rotate the element clockwise or anti-clockwise? Anti-clockwise, yeah. So it's tau xy here is 125 anti-clockwise. Okay, so that's my x point for generating Mohr's circle. Normal stress is 100, shear stress is 125 anti-clockwise. My y point then, sigma y is just 0, and tau yx Again, it's 125 megapascals, but this pair of half arrows here, the top and bottom of the square, would tend to rotate that element clockwise, wouldn't it? So that's 125 clockwise. Okay, so those are my 2 points for generating Mohr circle, and everything else kind of follows from that. So if you get those 2 points right, that's a good start. So I'll do a quick little freehand sketch here, just what I think it's going to look like. So my X point is going to be kind of out 100 and down 125. My Y point is out 0 and up 125. So my circle is going to look something like that, or my diameter is going to look something like that. And my circle is going to look roughly like that. So I'm going to draw that out to scale now, but I'll set the axis somewhere close to the left-hand side of the page, and just to have a rough idea before I sketch it out to scale, roughly what size everything is going to be, and I can work from that. Okay? Okay. Now, I don't have a ruler to hand. Does anybody have one handy? Yeah, choose that. I think these lines are not too bad. Okay, but I'm going to set my axis somewhere close to the left-hand side of the page. Again, that little freehand sketch of it there give me a rough idea of what it's going to look like. Yeah, we'll go something like this. Okay, so my X and Y points then. My X point was out 100 and down 125, and the Y point is out 0 and up 125. So this is tau clockwise and tau anti-clockwise down here. And then this is positive normal stress and negative normal stress. So tension on this side, compression this side, anti-clockwise shear down here, and clockwise shear up here. Okay, so my two points then, I want to go out 100 and down 125. So I'll go, say, 50 millimeters here. That's 100. And then down 125 would be 62.5 down here. Okay, so that's my X point, excuse me. That's my X down here. My Y point will be across 0 on the normal stress axis and up 125 on the shear stress axis. So about here. Okay, that's Y. So that's Y here is 0, 125, and this is 100 and 125 anti-clockwise. Okay, and everything else kind of follows from that. If you join those 2 points up with a straight line, that's the diameter of your circle. They should cross the axis here. The midpoint should be halfway between 0 and 100, so it should cross at 50, if I've done it correctly. I'm a little bit out in my line here. That should be crossing kind of here exactly at 50, but I'm a little bit out. Like 1 or 2 marks, not too severe. I think so. I'm not sure. We'll find out. Okay, so those 2 points, if you join them up with a straight line, that gives you the diameter of Mohr circle. Pop down your compass then, and you should get I'm out with something here. I'm going to check my measurements because that should be the same distance, and it's not. Excuse me. So what did I say? 125. I've gone different amounts anyway. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. I only went to 115, so I didn't go far enough with the X point. So the X point should actually be down here. And that would explain as well why they didn't quite cross the axis where I thought they should. So that should be more like that. We all make mistakes sometimes. Okay, so that makes more sense. Now that's crossing the axis exactly here at 50. And now I can pop down my compass and set the radius. Okay, so that's my radius there. And yeah, that looks a lot better. Probably could have left a little bit more room for myself, but there we go. That's Mohr circle done out. So the points of interest on Mohr circle are your maximum normal stress. So the very right hand side of the circle, that's your first principal stress, sigma 1. The very left hand side of the circle is the minimum normal stress, or your second principal stress, sigma 2. And they're located at some angle from your original XY coordinate system. Remember this straight line here, this diameter of the circle, that's your original XY coordinate system. So X on this side, Y on this side. So for example, my maximum normal stress is located at some angle. This is 2 theta. So it's at some angle anti-clockwise from my original X coordinate to this maximum normal stress, sigma 1. Alright? That's the same angle as from my original Y coordinate to my minimum, the sigma 2 down here. So that's also 2 theta. Okay? And you can pop down your protractor and measure what that is. That is about 68, yeah. So that's 2 theta is about 68 degrees. 68 degrees. So in the real world, the maximum normal stress, or that first principal stress, would be half of that. It'd be 34 degrees anti-clockwise from your original x-axis. Alright, so if 2 theta is 68 degrees, theta would be 34. And it's 34 clockwise, anti-clockwise from x to the maximum principal stress. You always measure your angles from your original x-axis to your principal stress. So the maximum principal stress would be 34 degrees anti-clockwise from x to sigma 1. And similarly, the minimum, or sigma 2 here, would be 34 degrees anti-clockwise from your original y-axis. All right? So that's one of the things we were looking for. We could sketch that out. I'll sketch that out here, maybe on the other side. So our original stress element was like this. It was sigma x was 100, and sigma or tau xy. Sigma y was 0. Tau xy was 125, and 125 for tau yx as well. Sorry, that's the wrong way there. In our new coordinate system, if we were to draw a new coordinate system, x and y, if we drew a new coordinate system rotated 34 degrees, so let's say 2 theta is equal to 68 degrees, theta is equal to 34 degrees, and that's 34 degrees anti-clockwise from xy. So if we created a new coordinate system, 34 degrees, from our original, and call that x1, y1. In that coordinate system, if you were to sketch a stress element like so, so 34 degrees rotated anti-clockwise from your original coordinate system, in this coordinate system you would actually have much more tension and you would actually have a compressive stress then sigma 2 this way. So whereas in your original xy coordinate system there was nothing happening, there was no stress in the y direction, in this new y direction there is going to be a compressive stress. And we didn't actually get the values off that circle there, but sigma 1 here, the stress is 184 maybe megapascals. Sorry, I'm going off the edge there. But yeah, I think about 184, so it's 92 on this scale, so double that, 184. And sigma 2 would be minus 44. No, sorry, double that, minus 84. Okay, so 184 and minus 84. So in this new coordinate system, in the new x-axis, you've got tension of 184 megapascals, and you've got, in your new y direction, you've got a compression of minus 84 megapascals. Okay? So in that new orientation, x1, y1.
Where are these values coming from?
They're coming straight from Mohr circle here. So if that's 0, normal stress, this is 50 normal stress, 60, 70, 80, 90, 100, 110, 20, 30, 40, 50, 60, 70, 80, 180, 184.
But you're changing the inclination of your plane.
Yeah?
And that underneath or is at, say, angle.
Do you mean this one here?
X-axis, yeah.
Yeah, that 184 megapascals is at 34 degrees anti-clockwise from my original x-axis, yeah.
And with that, before it's going to change, it's a combination of you're shearing or you're bending.
I'm not sure what you mean now. So if we go back and we look at the original shaft that this is based on. So in the original XY coordinate system, we said that there's no stress in the Y direction, there's about 100 megapascals in the X direction here. That X direction is not necessarily the worst case scenario. So what we're saying is if we took a little element off the shaft in this orientation, 30 degrees, 34 degrees from the axis of the shaft, in that orientation there's much more tension that way, and there's also a little bit of compression this way as well. Okay? And depending on what the shaft is made from, if it was going to break, it might break in that plane. So if it was made of something brittle like a ceramic or something like that, it might well break in that orientation.
So there are 2 theta calculation, that's the orientation of the plane on which the stress is maximized.
Yes.
And then when the stress is maximized, you take the maximum value, your bending stress off the x-axis.
When you say bending stress,
Or
the normal stress?
yes.
The normal stress, yeah.
Okay, right.
Yeah. Yeah, so the horizontal axis here is normal stress, sigma, and the vertical axis is your shear stress. Yeah. So at the moment, we're just looking at normal stresses. So this principal stress, this very right-hand side and the very left-hand side of the circle, they're the maximum and minimum normal stress on the part in any orientation. So that's the absolute maximum tension that's on the part in any orientation, is that sigma 1. And the absolute minimum normal stress that's on the part in any orientation is this sigma 2. Okay, and that happens to be, if you were to look at your shaft and rotator stress element 34 degrees anti-clockwise from your original XY coordinate system, that's where the tension and compression are the worst. Okay? Now, time is nearly up, but what was I going to say? Yeah, so that's your stress element there. You have 184 this way, minus 84 this way. In this orientation, there's no shear stresses. So shear is 0, 0, 0, and 0. Okay, so kind of at this point on your circle here, the vertical axis, you're 0. You're at 0 on the vertical axis. All right, so that's the principal stresses. The other one then, the maximum shear stress, you can get that off your graph as well. It's at the very, very top here, tau max. Okay? Or you could say down here at the very bottom of the circle, this is also tau max. Just one of them is clockwise and one of them is anti-clockwise. All right? The value for that, you can read it directly off your thing, but basically it's the radius of the circle. And the radius of the circle, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 20, 30, about 134. Okay? Or you can kind of read it with your ruler and double it. 134 clockwise up here, and 134 anti-clockwise down here. Okay? And that's the radius of the circle. Now, you could get that here, or you could use that value. If you said 50 plus 134, that's where the 184 comes out of. 50 minus 134, that's the minus 84, where that came out of. All right? So mathematically, you can calculate the radius of the circle. You'll be able to get sigma 1, sigma 2, and tau max if you can calculate the radius of that circle. All right? And kind of mathematically, I don't really have time to go through the whole thing now, but the radius of the circle, we looked at before, is the square root of sigma x plus sigma y over 2 squared plus tau xy squared, or tau yx squared, whichever you like. Basically, it's the hypotenuse of a right angle triangle where that length there is sigma x minus sigma y squared, I think. It's the difference between, or half the difference between sigma x and sigma y. So sigma x minus sigma y over 2 is that length, and tau xy is this length. Okay? So the square root of the sum of the squares of those two sides of that triangle there is the radius. And if you know the center of the circle and you know the radius, that will give you sigma x and sigma y, or sorry, sigma 1 and sigma 2. And if you know the radius of the circle, that's equal to tau max, 134. Okay? So your maximum shear stress is this point up here, it's 134. The orientation that occurs at, we call it phi, but 2 phi would be this angle here. Alright, so 2 phi, if 2 theta is 68 degrees, 2 phi here is 22 degrees, is that right? 22 and 68 is 90, yeah. It's 22 degrees. And they'll add up to 90 degrees. And it's 22 degrees clockwise from here to the maximum shear stress, or 22 degrees clockwise from Y to the maximum clockwise shear. Right? So if that's 22 degrees there, it's 11 degrees in the real world. So phi would be 11. So there would be some other orientation somewhere else. If this is your original XY coordinate system, if you had a coordinate system that was 11 degrees clockwise to that, like this, so call that X2, Y2. So this is 11 degrees clockwise from your original XY coordinate system. If you were to draw a stress element there, and notice that this here is 45 degrees to this one. So it's 90 degrees different on the Mohr circle, it's 45 degrees different here. So 34 degrees anti-clockwise from X and 11 degrees clockwise from X. They're 45 degrees apart. So anyway, in this orientation we have a shear stress of 134 a shear stress of 134 clockwise on the Y side and 134 anti-clockwise on the X side. So 134 clockwise on the Y side would be, clockwise is this way. So that's 134 clockwise. And on the X side, 134 anti-clockwise this way. Okay? And then what about normal stresses in this orientation? We go back to here. What's the normal stress at this location? What's the normal stress here in this orientation? It's 50. So we're straight over the center of the circle, so that's 50. And what's the normal stress at this location? Is also 50. So what you would have here on your stress element is, this would be 50, 50, 50, 50. So your stress element where the shear stresses is a maximum, it's 134. The normal stresses are all balanced, they're all equal and pointing out in all directions. So it's like a hydrostatic stress where the stresses are balanced. The X and Y stresses are balanced, but you have lots of shear stress in that orientation. And that's kind of going back to your shaft here. It's if you were to just take a little stress element somewhere oriented 11 degrees clockwise from your original, it might shear off there.
All done?
All done. Yeah. So it's 5